All right then. Next, we're going to look at intensity in the double slit interference pattern. Okay, so our goal here is to determine the intensity of the light at all points in the pattern. Now, what we can do here is we can assume that the intensity of the light at any point is proportional to the score of its wave amplitude. And if you remember in the electromagnetic chapter, we talked about where the intensity was proportional to the electric field square. Remember the intensity, basically average Poynting vector, and average Poynting vector was proportional to the electric field square. That means electric field vector at any point P will be the sum of the electric field vectors of the waves coming from, slit 1 and slit 2. That means we can write the electric field 1 in terms of E10, where E10 is the amplitude of this electric field 1, then times sine of omega t being the angular frequency. Then E2 is equals to E20 sine of then omega t plus delta, where the delta here is then the path length or the phase difference, right? So I can say that delta here is the phase difference. Okay. So the obviously now what we have here is the phase difference. Basically tells us that extra, distance that wave 2 has to travel relative to wave 1, for example. And let's say for if I choose point of interest to be exactly uh, at the center, then if I use, let's say, distance from the slit 1 and distance from the slit 2, then what I will get here is exactly same distance. So then this delta will be 0. So delta equals 0 for the center of the screen, basically that point 0. Okay. Now, if then path length, if the difference in path length from P to S1 and S2, that means, I have now different point P, right, is, for example, is d sine of theta equals lambda over 2, then the two waves are exactly out of phase. That means, this d sine theta equals lambda over 2, which is basically, we can say that this is then, they're out of phase, so then delta is equals to pi, or 180 degrees. That means they're out of phase by 180 degree or by pi. Okay. Now, this is if. So, but if the, d sine theta is equals to lambda, then what we have here is the two waves differ by a phase of 2 pi. So 2 pi. Okay. That means what we have here is that in general, delta over 2 pi will be equal to then d sine of theta divided by the lambda. Okay. Then from here we can rewrite in terms of delta, which is uh, the phase difference. So then delta will be equals to, so rearrange that equation to the left. So it will be 2 pi d sine of theta divided by lambda. So then this will be basically equation for the um, phase difference. Okay. All right, so then what we have here is electromagnetic wave, right? So basically the electric field at that point P will be pretty much a vector sum of electric field of, E1 and E2. That means we can say that this electric field is E1 plus E2. All right, so one of the things we do here is then very similar to the AC circuits when we were dealing with uh, voltage and current, and we learn about phasors. So where we can use this phasor diagram to add, let's say, the scalar components of those vectors. Same thing we can do over here, because one thing we can see here is that we have E10, which was the amplitude of that vector E1. E20 is the amplitude of the vector E2. So we can basically add them together like this as phasors. Okay. That means what we can see from here is that if I'm looking at the projection of them on the y-axis, so this becomes basically E1, and then this becomes E2. Then what I have here is that E as a function of theta will be sum of E1 and E2. Okay. So that means if I then add those two together, then E theta is equals to E theta 0, which is basically this guy over here, right? The amplitude of that hypotenuse of the, sum of the amplitude of the E1 and E2. Then sine of omega t plus delta over 2. Okay. Well, over here we can see that this angle phi, so technically this would have been, angle phi, but from here we can see that phi is equals to delta over 2 using the symmetry. So since phi equals delta over 2, then here I can write this as delta over 2. Okay. Now, one thing I have here is then the amplitude of this vector, of this E theta. So E theta 0. Okay. So I can use then, for the amplitude, I can then combine E1 0 and E2 0. And I can see if I look at their projection, so for example, their projection on the x-axis, so then technically that's a projection of the x component of those. So I can rewrite this as 2 E naught cosine of phi, or 2 E naught cosine of, well, phi is equals to delta over 2. Again, remember, phi is equals to delta over 2. All right, so that means this is the amplitude. So this is basically just this guy over there. Then I can combine E theta is equals to amplitude written as E20 cosine of delta over 2, then times sine of omega t plus delta over 2. Okay, that means then this will be the equation for the the electric field amplitude. So electric field is a function of theta. Now, but we also would like to get the equation for the intensity. So for the intensity, then I can write the intensity ratio. Since intensity is proportional to the electric field square, I can say then there's intensity as a function of theta divided by its amplitude. So it equals to then E theta 0 square divided by 2E naught square. So then this basically will be equals to cosine square delta over 2. And kind of combining those, going back and using those two equations, we can basically divide them and get cosine square delta over 2. Again, if you're, this is because intensity is proportional to electric field, right? That means, I naught is proportional to E1 naught plus E2 naught squared, and then I theta is proportional to E theta squared because of the intensity is proportional to the electric field square. All right, so rewriting then this equation, then I can say I theta is equals to I naught then cosine square delta over 2. All right, so cosine square delta over 2. And then remembering that a few slides before this, I defined delta, the phase difference to be 2 pi over the wavelength times d sine of theta. Then I can rewrite this as I theta equals then I naught, then cosine square. So then for, replace delta with that. So I can rewrite this as cosine, then you can write it's delta over 2, where delta is 2 pi. So technically the 2 cancels out. So what I have here is pi d sine theta over lambda. Okay. And then this is basically squaring. Okay. All right. So then what we can do from here is this, because if you have a double slit, and you have then the screen, this being the length L. So we always talked about that the theta here, right? This theta is very small. So theta being small is approximately sine of theta, approximately tangent of theta. And then y was equals to L tangent of theta. That means tangent of theta was equals to y over L. Okay, since it's equals to y over L and tangent of theta equals y over L, and for a small angle, tangent of theta is approximately sine of theta. So I can say sine of theta is basically is also equals to y over L. Then come back to this equation where I will replace sine of theta inside with ratio of y over L. Then I can have I of theta is equals to I naught, then cosine, then what I have pi d, and replacing sine of theta with y over L. So it becomes y over lambda L. And then this whole thing squared. Okay. So then this will be our final equation for the intensity. And then I can also say that this is when the distance from the slits to the screen, that means this L, is much greater than the position of P, right, on the screen where we have, let's say, this particular point of interest. That means Y is much smaller than L, okay? And also D is much smaller than L. That means this D here, the distance between the slits, is very small compared to the length L, because we assume that where the slits are and where the screen is generally like, let's say, uh, around on average around a meter distance. So a meter, maybe meter and a half, where then the distance between the slits is always in millimeters or micrometers, and then same thing with the vertical position y, generally in millimeters or micrometers and things like that. So they're always much smaller than few meters, let's say for the L. All right, so then from here, what we can do is we can see that if we plot the intensity as a function of angle, we basically get a graph like this, right? So where we have then, this is the amplitude, right? I naught. And this one shows that pretty much intensity pattern assumes that most of them, let's say the maximus are going to be the same intensity, right? As the central one. And for the double slit is, um, at least for some of the nearby patterns are that could be true. Central one will being a little more, let's say brighter than the other ones. But one thing we will see in the next chapter is that when we're considering a single slit, for example, that actually not quite true. For the single slit, the central bright is much brighter than the subsequent, maximus, and it's basically the screen is dominated by the central maxima. All right, let's look at a couple of examples here. So we have two coherent microwave sources, both produce waves of wavelength 1.5 centimeters. The sources are located in the z equals 0 plane, one at x equals 0, y equals 15 centimeters, and the other one x equals 3 centimeters, y equals 14 centimeters. If the sources are in phase, find the difference in phase between the two waves for a receiver located at the origin. Okay, that means we assume that since we are told that they are in phase, we can think of, let's say that, let me use this color here. So then delta will be equals to delta R over lambda times 2 pi. Okay. So that means this will be then the difference in phase, right? It will depend on the path difference according to this equation. Okay. Now the path difference is the difference in the distance that one wave has to travel compared to the other one, right? That means one thing we have here is, let's say if I'm doing x, y, and z. So one is given x equals 0, y equals 15. So let's say somewhere over here. The other one is given x equals 3, y equals 14. So maybe somewhere over there, right? And then what we have here is, let's say, then our basically the receiver here is located at the origin. That means one is going like this, the other one is going like that. Okay. That means we have to basically find the, the path length difference. So then we can think of it like, let's say, in terms of this is being, let's say R1, this is being R2, or, let's say this is R2, this is, this is R2, this is R1. Doesn't really matter. So we're just basically looking at the delta R. So the delta R is their difference. So then this will be 15 centimeters minus, this distance over here, which we can use a triangle, right, to find that, since this is 3 centimeters, this is 14 centimeters. So that's basically square root of, using the Pythagorean theorem, right? It's 3 centimeters squared plus 14 centimeters squared. And then we find the difference. So then delta R will be equals to 0.682 centimeters. All right, so we got that. Then we can come back here and using this equation, delta equals then 0.682 centimeters divided by the wavelength, which is 1.5 centimeters. So then the units cancel out as a centimeters. Then we have then 2 pi times 2 pi. That means our answer will be in radians, which is basically the appropriate one that we want. So this will be then 2.9 radians. That will be the answer for the difference in phase between the two waves. So 2.9 radians. All right, so here's one more example. So a monochromatic light is incident on a sheet with a long narrow slit, and let I naught be the intensity at the central maximum of the diffraction pattern um, on a distant screen, and let I be the intensity at the second intensity maximum from the central intensity maximum. Um, that means what we have here is I naught is the intensity at the central maximum, and I is the intensity at the second intensity maximum. That means M equals 2 for the second intensity, right? So the first, um, because the first intensity maximum from the central one is M equals 1, and then the second one M equals 2. All right, so then distance from this second intensity maximum to the far edge of the slit is longer than the distance from the second intensity maximum to the near edge of the slit by approximately 2.5 wavelengths. What is the ratio of I, this should be O, of I to I naught? All right, that means what we can do here, we can evaluate the expression for the intensity. Let me see. I just realized that this is actually a single slit, not a double slit. So this example should have been in the next chapter. But in any case, I'll go ahead and solve it. So here what we have, the equation for that is I is equals to I naught, then sine of 1/2 phi divided by 1/2 phi, which is basically that's the equation for the intensity of a single slit. So and in this case, what we have here is the phi here is pretty much the phase difference. So taking the ratio, dividing basically both sides by I naught, then we get that. Okay. So then here, the phi here is equals to 2 pi over lambda a times sine of theta, because this is a for this distance to be a, because this is a single slit. Okay. Now a sine of theta is equals to 5 over 2 a wave 5 over 2 times lambda, because here we do like 3 plus 3 plus 1/2. So we do the 3 plus 1 half times lambda, so we get 5 over 2 lambda. And so then phi here is equals to 2 pi over lambda times a sine is just basically then 5 lambda over 2. Lambdas cancel out, 2's cancel out, and we get 5 pi. Okay, that means then we can come back here. I over I naught is equals to then sine of um, 1 half phi, where phi is pi over 2. Sorry, phi is 5 pi. So 5 pi over 2 divided by 1 half 5 pi. And finally square this, then to get the ratio of 0.0162. There we go. All right. So the next thing we have here is the interference in thin films. Okay. So this is pretty much another application of where you see interference of light. So you can see this is one of those everyday applications that you can see, right? So this is one of those beautiful phenomena when you see the soap bubbles, right? Or a little bit of oil on the on concrete, then you see that beautiful colors. So these are those basically is due to the fact that light constructively and destructively interfere when it reflects off of two different surfaces. So we're going to be, seeing that what we have here is, for example, when there's a, when there's a oil usually, like let's say, on top of some kind of other surface. So either like concrete or maybe there's a water or something like that. So then what happens here is, uh, let's say that this is the incident light over here, some kind of source. Then the light is incident at point A. So then what you have here is you have three different mediums. So you have air, and then you have oil on top of some water. Okay, so that means you have air, oil, and water. Those are our three different, basically three different mediums. So remember, so generally N, let's call this N1, right? So this is, let's say, 1 because it's air. And 2 will be oil, which is generally water here is 1.33, but oil always has a little bit less index of refraction. So let's say 1.2. So maybe like 1.2 is appropriate for that. Now, one thing we have is then, let's say you get then two different reflections. So one is with point A, when you can see that a light ray traveling from air incident at point A. So then the sum of the light will be reflected. And that's basically this light over here, right? The reflected light over there. So that's a reflected light at point A. But then some will refract because what you have oil, right? Some will refract. Okay. Now, if you're an observer looking from here, then what you see here is that you will see that reflected light from point A. But when the refracted light hits point B, then it will also reflect. Some of it will reflect. So when it reflects, then at point C, it will then come out, from oil, basically to reflect back to oil, then from oil to come out into the air. Then this will be then the light, basically the second reflected light. Okay. That means you have basically reflected ray 1 and reflected ray 2. Okay. And one of the things we have here is they will basically undergo at this point, right? Some phase difference, right? Phase change. But one thing we can say here is the way what you will see here is it will be constructive interference. Okay, so it will be constructive interference, and then you will see then a bright color. So that's why when you look at the soap, right, you see some kind of bright color. One thing we can do, we can take that, for example, this distance to be t, like the thickness, and remembering that the wavelength lambda n is equals to lambda over n, where lambda is the wavelength of the light in vacuum divided by the index of refraction in this in this medium over here. So one thing we can see here is this. So for example, then a constructive interference, right? So for the constructive interference condition will be when light going this distance 2t, right? It covers, it goes down 1t, comes back 1t. So that means, it covers this distance 2t. When this 2t is equals to then m plus 1 half times lambda n. Okay. So then this will be basically the condition for constructive interference. Okay. Right. Since then what we have here is I can rewrite lambda v, which is lambda in vacuum or air. So I can just basically drop it without the subscript, means it's vacuum or air. Then this is equal to then let's say lambda n times n, right? So I can write like that, or I can say, in terms of if I take this lambda n, replace it with lambda over n, that means what I have, lambda n is equals to lambda over n. That's what I can have this one. 2t is equals to m plus 1 half. Then this will be lambda over n. And I can also move this 2 and t is equals to m plus 1 half times lambda. Okay. So this will be the condition for constructive interference. Okay. So which means that uh, if the, let's say the phase difference for the waves, um, for two waves, right, is m times lambda, and they are 180-degree phase, there's 180-degree phase change between them. Okay. And one of the things we have here, we're going to talk about, let's say, some condition where the light, when it goes from lower index of refraction to higher index of refraction, then it actually uh, undergoes a phase change. So, but what we have here is, the first ray, when it goes from N1 to N2, it basically reflects off of the N1 and N2, the surface. N1 is lower than N2, so ray 1 undergoes 180-degree phase change. At point B, ray 2 goes again from N2 and N3, but again, that point B represents reflection from a lower index of refraction to higher index of refraction. That means again this light will also undergo 180-degree phase change. That means both ray 1 and ray 2 will be 180-degree phase change. That means when you see those as an observer, right, when you see that those two lights, they both have been switched, sort of, like, let's say, but both of them basically have the same crest and same troughs, because both of them 180-degree you know uh, basically have a reflection phase change upon reflection. I'm going to talk about it in a little bit. But in terms of then what we see here is, because for both rays the index of refraction of the previous medium is lower than the next medium where they reflect off of, right? They both undergo 180-degree phase change upon reflection. That means both of them then in phase, because both of them have undergone the same exact phase change. Okay, so that means in this case we will see that. But then what we can also have here, the destructive interference condition. So for that, what we'll see here is 2nt, that will be equals to m times lambda, and that will be the condition for the destructive interference. Now, one thing we have here is that m is then the order is equals to 0, 1, 2, 3, for both of them. Okay, so both will basically undergo that. Okay, so this is another application of that, but this time what we have here is that a similar fact, but you have a curved piece of glass on top of another glass, so you can see, right? And one thing we have here is that you can still have the same two types of reflections. So for example, if I have the ray moving like this, so then I get two reflections. So one is right here at point B. So let's say, so we're going to look at that one. So That means, we have one over here. So then this is ray one reflects. And then another one going to be right here at point C. And then this one reflects. Okay. So then what we have here is that here you're going to absorb, again, same thing, right? So we're going to absorb a constructive interference. So let's say this will be one of those lines over there, right? But then what we can also have here is another point here, point A. That means when the light, kind of like, let's say, reflects off of here, right? Then you can see, right, at the center is that when they're both basically in contact, point A where the, a curved glass is in contact with a flat one, you see a destructive interference. So basically you see a dark spot. So that means, there's a bright spot here. That means they constructively interfere, and there's a dark spot. So by the way, this is known as the Newton's rings. Okay. So for Newton's rings, then what we have here is the difference between, let's say, this BCD, let's say, wave and one at A, is that there is an air gap between, point B and C. Okay. That means one of the things we have here is this air gap. Then um, what it does here is for point C, right? When it reflects off of that, it basically gives you pretty much, a same condition. Okay, so we can see that from the slide over here. That means the beam of light reflected whenever it goes, let's say, so this is the incident, incident ray or incident wave. So N1 is then the medium where it's incident. Then it hits this boundary line. Now, if N2 is greater than N1, the reflected light will be out of phase. See where there was a crest, now there's a trough. Okay. But when incident light hits a boundary line where the N2 is less than N1, for example, from glass to air, then there is no phase change, right? So there is no phase change. Okay. That means what we have is that the beam of light reflected by a material with index of refraction greater than that of material in which it's traveling changes phase by 180 degree or half a cycle. All right, so let's look at this example here. A soap bubble appears green, wavelength of 540 nanometers, at the point on its front surface nearest the viewer. What is the smallest thickness the soap bubble film could have? Assume n equals 1.35, which is basically the uh, for the bubble. All right. So one thing we have here is that let's say if I take this to be point A, over there you go from lower index of refraction to higher index of refraction. So that particular reflected ray will undergo 180-degree phase change. Okay. Well, where the other one will not undergo. Okay, that means what you have here is, in one case you will have, in other case you won't. That means um, this one at point B, for example, will not have a phase change because N2 is less than N1. That means when it, let's say for B, N1 is basically a bubble, and 2 here is air, right? So where for A, N1 is air, N2 is then the bubble, sort of like that. Okay. That means one thing we will have here is the smallest thickness for the light will be in terms of when M equals 0. So remember, we want to, be able to see the green color. That means we want to see constructive interference. So that means this is 2t is equals to then M plus 1/2 lambda over n. But since M equals 0, so this becomes 1/2 lambda over n. That means we want to see, like, let's say, what will be the thickness, and that means just basically solve for the t. Then t will be equals to uh, wavelength over 4 times n. So then the wavelength equals to 540 times 10 to the negative 9 meters. divided by 4 times index of refraction of the bubble, so 1.35. We calculate that, so we're going to get 100 times 10 to the negative 9 meters, or 100 nanometers. Okay. That means this will be basically the first constructive. And the second constructive will be additional, 200 nanometers in thickness, and so on and so forth. But this, remember, because we want a constructive, right? We are looking at constructive interference equation. Since it's the first constructive, m equals 0, because this equation, right? Assume that you have this equation, right? So m equals 0, 1, 2, 3, dot, dot, dot. This means the first one is when m equals to 0. All right, so in any case, so for the interference in thin films to solve those problems, you can see that interference occurs when two or more waves arrive simultaneously at the same point in space. Constructive interference occurs when the waves are in phase. Then that means you can say that it's 2t is equals to m plus 1/2 times the wavelength over n. And then destructive interference occurs when the waves are out of phase. That means what you have here is 2t is equals to then m lambda over n, or basically 2 and t is equals to m times lambda. Same way 2 and t is equals to m plus 1/2 times lambda. So both are the equations for those. Okay. So an extra half a wavelength shift occurs when light reflects from a medium with higher refractive index. All right, but there is a very important thing to understand about these equations. So each equation can be for constructive and destructive interference. And that depends if you get one of the rays reflected that is, um, let's say, undergoes a phase change, or both of them undergo phase change. So let me write that down over here. So think like this. So this equation 2nt is equals to m plus 1/2 times lambda. So I said that this is for constructive. Okay. So that means this is constructive, or constructive. So this is constructive, basically, if only one reflective phase change. So constructive if only one reflective ray undergoes a phase change. Only one phase change. Okay. But then this becomes destructive with either 0 or 2 reflective phase changes. That means, sort of like, let's say this equation has two conditions. Condition 1, that's an equation for constructive if only one of them undergoes phase change but not the other one. That's why I used this for the previous example. But then what I have here is it can be used for then the destructive interference if 0 or 2 phase changes. That means none of them undergo phase change or both of them undergo phase change. Then that equation is used for the destructive interference. Okay. So that's that. Let me write that down. So C constructive for one phase change, and D destructive for 0 or 2 phase change. All right, so how about the other equation, 2nt equals m times lambda? Well, this is, this is what I said, that this is for the destructive, right? So use it for destructive. But I assume that this is D for destructive if one phase change, but this is for the constructive if 2 or 0 phase change. Okay, that means you need to understand in terms of where is this thin film is, right? Is a thin film between air and air, or between, let's say, air and water, right? So then you get basically different things, right? So you have two rays that being you have two rays that are being phase changed, compared to just one of them, let's say in one of the examples. That means, when you have air and you have then thin film, like oil or something like that, and then water, that basically you have both of them, right? So if I kind of go back to right here, that's what I have. So because it goes from lower to higher, there is a phase change. Okay. Again, here it goes from lower to higher, there is a phase change. That means you have two reflective phase changes. That means what equation should I use over here? Well, 2t is equals to m lambda over n. Then this equation for the constructive. So this is for the constructive, then the other one for the destructive, because I have uh, um, two reflective phase changes. Okay. So then that's why, for example, remember, right? So when n2 is greater than n1, you then have a phase change. Okay, so that means the reflected light is out of phase. Okay, but then when you go uh, n2, which is less than n1, which we had in this example, right? So let's say for this particular phase, right? So you have n1 and n2, and obviously n2 is less than n1 because air is less than bubble. That means light reflects, and then you have just one reflective phase change. That's why I used this equation, because this is a constructive for just one reflective phase change. Okay. All right, so that's kind of like important thing to understand, right? So that means each equation can be switched, reversed, depending if you have one reflection or reflective phase changes or two reflective phase changes. So you have to be a little bit careful over here, but obviously then you have to look at that index of refraction. So always take the, your let's say thin film, whatever it is, right? The bubble, let's say for example, right, or oil or something like that, and then see what's above and below it. Will it, undergo two phase changes or only one phase change? All right, so here's one more example. So you have a non-reflective coating. So it says, what is the thickness of an optical coating of um, magnesium fluoride whose index of refraction is n equals 1.38 and which is designed to eliminate reflected light at wavelengths in air around 550 nanometers when incident normally on glass for which n is equals to 1.5. All right. So what we have here is, this coating here is our thin film. Okay. So then we're given index of refraction of that to be 1.38. Okay. So with 1.38, then what we have here is, so you have things like this. So this is air. So you have 2 points of interest. Okay. So this is air. So and in this case, what we have here is you have light going from, I can say this is N1, N2 for this particular, point A. Let's call this point A. Okay. So then the question here is, will there be a phase change or not? Okay. So, well, obviously, this is going from lower index of refraction to higher index of refraction. And when it goes from lower index of refraction to higher index of refraction, there is a phase change. All right. So that means ray 1 will undergo a phase change. And then we have a ray 2. Well, here we also go from low index of refraction, 1.38, to high index of refraction, 1.5. That means, again, N2 is greater than N1. Let's say for point B, this is N1, this is N2. It means, again, there will be a phase change. Okay. That means what we have two reflective phase changes. Okay. And which means that in order for us to see basically the, in terms of the color, right? Sorry, eliminate the color, right? Um, we want to eliminate. Um, we want to basically look at distractive interference. Okay. So that means this is a distractive interference, and we need to use the equation for the distractive interference, but one that has two reflective phase changes. Okay. That means ray 1 and ray 2 will both undergo phase change. So that means the equation for the distractive interference will be a 2t, then m plus, sorry, 2t is equals to m plus 1/2 times lambda over n. Again, remember, it's always m equals 0, 1, 2, 3, and so on and so forth. So looking at where m equals 0, this equation becomes 2t is equals to lambda over 2n. Then using this, we can then calculate for this specific t, right? So then t is equals to lambda over 4n. So then lambda here is 550 nanometers divided by 4 times 1.38. And then we calculate this, we should get then 99.6 nanometers. And that will be the answer for this. All right, so the next few things is just kind of like a optional extra information. Here we have a Michelson infra interferometer. Sorry. So this is just an experiment that allows us to basically be able to make a very precise measurements of length. So here we have some kind of source, so some kind of light source that is incident to some kind of mirror that has a specific coating, so like a silver coating that absorbs about half of the light, okay, and only reflects other half. That means it reflects the half of it, but then the other half just can go transmit, through the mirror. Okay, that means the one that is reflected goes like this and hits some kind of a movable mirror. Okay, so then the light goes, hits the mirror, and then reflects back. The same thing with the fixed mirror. It goes, hits, and reflects back. And then what you see here is then that reflected light will those reflected light will combine and basically move toward the observer. Okay, but one thing we can have here is the because of that movable mirror, half the time we will see a constructive interference, the other time destructive interference, depending on what is the position of that movable mirror. Okay, and then it will allow basically to get a precise measurement of the length. Again, so some of those something that we don't really look at in great detail, but interesting application of that. And the last one here we have luminous intensity. So this is um, basically looking at the intensity of the light, which we looked at before in terms of the pointing vector. But obviously, when we're talking about human specific, right, we want to look at the one that is actually relevant to us, the one that we can actually see, and we only can see the visible spectrum. That means this is the intensity of light perceived, depends not only on the actual intensity, but also the sensitivity of the eye at the different wavelengths. That means we only can see that, from about 400 nanometers to about 700 nanometers. So then what we do here is we have this sort of like a new unit, a lumen, where one lumen is equals to 1 over 680 watts, or of 555 nanometer light. Why 555? Because our eyes are mostly sensitive to that. Right, so that's basically the luminous flux. So sometimes when you go and buy a light bulb, you might see that it's given in terms of lumen. So greater the value of this, right? Let's say 20 lumen, 30 lumen, 100 lumen, the brighter the light bulb. Then we have luminous intensity in candela. That's 1 lumen per steradian. And illuminance is the luminous flux per unit area. All right, so that should then conclude this chapter.